Well, tension members, I believe, are worthy of special consideration. As a construction component or as a component to construction projects, they are very valuable because they are extremely strong for their weight compared to compression members. For example, if you had a couple of people and they're separated by some distance and they're holding on to some string, and let's say that they're pulling it this way, there's some tension in the middle. Does it matter how long that string is for that tension to be there? In other words, no, the string can be 2 feet or it can be 200 feet, and in general the tension is going to be the same if the people pull with the same force. You can't do that with compression members. If you have a thin compression member, it will tend to buckle. And the only way to make a thin compression member less likely to buckle would be to make it thicker, which obviously means you're making it heavier. And so compared to compression members, they are extremely strong for their weight. And they're often used in combination like this bridge, or like this member here, where you may have 3 members with 2 pins, and with they may tend to go side to side here, become a parallelogram, unless you put a tension member in here. You're making it into a triangle. If you could make that a compression member, and then it would be rigid in both both x and y force. But you can see that if you put one there, it would resist force. I guess it would resist force going in this direction pretty well. If you put one here, it would resist a force going in that direction. But if you put them in both places, then you have a nice rigid structure where if you push it in this direction, one of the one of the strings tends to become tight and the other one may become slack. If you push in the other direction, one of them will be tight and the other one slack. But again, this is a very common and very powerful way of building strongly supported structures. All right. So tension members have the same strength virtually independent of length, and that's not totally true. Obviously, they're longer, they're going to get heavier, but most of the time, the length and the weight of a tension member doesn't really come into that much of into play that much. All right. Let's just look at a couple of tension members. This is extremely common in construction materials and in construction machinery, like these cranes. They have got these long strings that are tension members, and clearly they're able to support a lot of weight for their weight. And telephone pole guy wires are like that. These are actually tension members, the actual telephone wires themselves, but the guy wire is a very thin, very lightweight way of supporting things. You can't really see this structure too much, but this is if you zoom in on it, maybe you can. Well, let me zoom in on it. Here we go. You can see that this is a fence post, and it's supporting a fence on both sides. But to keep it from becoming a parallelogram, you put these two X forces right there, or the 2 wires, and then that stays nice and steady, and it won't become a parallelogram on you, regardless of how much force you're pushing on it. Let me get that out of the way. And here's something at the Boise State Stadium. Maybe you've seen this, but these light standards are way up in the air, and they're really, really big. But you can see that they got these little X's up here, and what these do is makes this a nice, lightweight, very rigid structure. One of the wires, in this case, keeps from becoming a parallelogram in one way, and the other directions keep it from becoming a parallelogram in the other way. And you can see a little bit of a zoom in on that one. Gates are very, very common. When we do this, we don't care about we just care about one direction primarily, but if you have a gate that looks like this with a support here, it's going to sag over time, and this point would be dragging on the ground. So what you do is you put a nice lightweight tension member there, and it keeps this corner from dragging on the ground. Same thing over here. Here's the hinge over here, and that's a tension member right there. Oops, sorry. There's the tension member right there. And actually, this is one I built at my house. This is a 3-rail vinyl fence. I just had to build a very small section here, but what we have is a steel wire with a turnbuckle, and it's mounted to my house here. And basically over time, even though these are supposedly rigid connectors, after a while they do become and look like pins, and this whole thing is going to sag, and this would be dragging on the ground here if it wasn't for this lightweight tension member basically going from that side and pulling it up. Here's another gate that's interesting. I thought this has 2 diagonal wires, and it works kind of the same way. So how do we analyze things? Again, a gate has a very common failure mode. It becomes a parallelogram over time that looks something like this. Reinforcing with a diagonal tension member is common, prevents sagging. Gates, in order to solve this as a statics problem, we will model this as a pin joint problem. We're going to say those are pin joints there, and to find out the tension, we're going to say that this one has to be a pin and that one has to be a roller. We already talked about how that is the only way to statically determine that. And then we model it as a non-rigid body and break it apart. So here we're treating it as a rigid body in order to find the reactions. We're going to say that there's a weight kind of coming in the center of the gate, and then we're going to break it apart and model each individual piece as a weighted member by assigning half of the weight to each member and then to the ends, which is at the joint. So again, I'm going kind of quickly here, but this is kind of the way I would suggest you're doing things. So let's say we have a gate here, it's very simple. That's 5 feet by 4 feet. It's got a pin here and a roller here. Let's say that the members weigh 1 pound per foot. So that means this weighs 5 pounds, this weighs 4 pounds. And then what we're going to do is take half of the weight, assign it to each end. So this 5 pounds, I'm going to say that 2.5 pounds is going on each end, 2.5 pounds on each end. This 4 pounds, I'll say that there is 2 pounds going on each end, and similarly with those 2 members. And then we're going to put it back together and say that this has 4.5 pounds, this one has 4.5 pounds, 4.5 pounds on each corner. From there, now we can break it apart using our either method of joints or method of sections. So what we've done is kind of pretend that it's a rigid body to find the reactions, break it apart to find out the forces at each point, and then break it apart using either method of joints or method of sections in order to find the tension in that diagonal member. So you can see kind of how I did it there. This is either way works, and I think you'll find that this is pretty valuable.